Hi, everyone. We're Group 37. This is our ML final project. Our project was on AMEX default prediction, and our group members are Hassan, Aditi, Emma, and Amrit. Next slide. So first, some introduction on our problem. 70% of Americans use credit cards for their regular transactions. And via using their credit cards, they also generate credit scores, which those who loan money also used to assess the risk of consumers defaulting on their credit card statements. And so it's important to assess credit card default risk so that lenders can best identify who to loan money out to, and buyers can also best represent themselves via their credit scores. Based on this background, we chose the problem of improving the existing models for credit risk assessment that AMEX has. And our goal was to both identify the features that best predicted credit default risk and more accurately and efficiently predict credit default risk. Next slide.
We obtained the dataset from the AMEX credit card default prediction competition. There are 5 million data points. Each row corresponds to a user's data. There is 191 features, which has been normalized. 178 of them are numerical. One of the features is a date time. The features are classified into 5 different types: delinquency, spend, payment, balance, and risk. Next slide.
We perform exploratory data analysis and find that major chunk of certain columns had missing values. We also compare train and test data variance and skewness. The distribution of the data was similar for most of the columns except for the ones shown here. Uh, and we, as we will see later, these features tend to contribute less in the feature importance of our best models like XGBoost. Next. So we perform the data preprocessing for imputation of the missing values. We group the data by the customer IDs and replace the missing values by the mean of that specific customer. For the remainder of the missing values, we replace them the overall mean or zero. And for later on, we perform the aggregation of the data points for each customer uh, by replacing the aggregate of the entire data points to the mean of the entire value. And we also perform certain further feature processing, which is specific to the methods that we use. Next.
So we started with unsupervised methods to better understand the shape of our data. And we ran k-means and GMM to visualize our data and how the data clusters related to one another. And we also did dimensionality reduction with PCA and TSNE to identify the most relevant features to predict credit default risk. Next slide.
We look into the dimension and externality method for data visualization. Here we see 3 components of the PCA, which is a linear dimension reduction method, and TSNA, which is a non-linear method. We can see that the classes are not linearly separable and there is a significant overlap in the clusters.
We use PCA to do dimensionality reduction. Our PCA analysis reduced the original 191 features to 100 PCA components to account for at least 95% of the variance in the data. On the slide is a visualization of every pair of PCA components in the top 7 PCA components. The visualization showed the nonlinear separation and overlap of the two classes, default and compliance. The supervised model and parametric unsupervised model are ideal candidates to handle this type of nonlinearity. Next slide. Next, for unsupervised learning, we use k-means to model our data set. We evaluate the performance of the model. We look at both internal matrix and external metrics. The CLS score is close to 0, suggesting that there is an overlap between two clusters. This matches what we have seen in the PCA component visualization, where we see an overlap between compliant and default class. The beta CV value less than 1 suggests that the data within each cluster are close together. For external metrics, our k-means model predicts a sample with the default labels very poorly, with a precision score of 69%. However, the compliant cluster has a high precision score of 92%. because of this high precision score, the overall accuracy of our model is the 85%. This accuracy score is misleading because it hides the fact that the model is not good at predicting the default label. As a result, we decided that the k-means is not a good model for our data set. Next slide.
So because our data might not be spherically distributed and the covariance between features likely impacts the clusters they belong to, we also ran GMM on the PCA reduced data. And we ran 5 GMM models, each on an increasingly large subset of the feature space. And each of these increasingly large feature spaces represented larger variance represented in the PCA features that we ran the GMM models on. And we saw that there were a similar distribution of the GMM data on the smaller feature sets as the larger feature sets, which indicated that we might not need to keep all the PCA reduced features for further supervised and unsupervised learning. And the labels for this problem are also probabilistic, so it made sense to understand the cluster responsibilities for the compliance and default clusters via GMM. And the metrics are also captured here. So importantly, the silhouette score is better than that of k-means. And this is likely because we ran GMM with the 2 clusters, and this caused the points in the clusters to be more well defined by each Gaussian PDF than if we had ran GMM with additional clusters. And the recall and accuracy scores were similar for both clusters, but the default cluster had a lower precision and F measure score, which is likely due to the fact that there's more compliance data that our GMM model ran on compared to default data.
So we used 2 types of supervised learning methods. The first one was gradient boosted trees, and the second one was feed forward neural networks. Some additional pre-processing needed to be done to help predict loan default. So depending on whether the variable was binary, categorical, or continuous, we used different aggregations and missing value imputation techniques. This added up to a total of 724 features that we could feed into our classifier. So the neural network had 2 layers. The first one was a fully connected dense layer with 64 hidden units. And the second one was the output layer, which was followed by a softmax activation. These added up to a lot of parameters, but we had a lot of data, so we could afford to do so. The evaluation metric defined by AMEX was the average between the normalized Gini coefficient and the default rate at 4%, which captured the sensitivity and recall statistics. Our models performed reasonably similar to each other, so we got accuracies around 0.78 according to their M score. This was slightly short of the 0.8 achieved by competition winners for the same task. And the feature importances were found using XGBoost. Yeah,
So the final conclusion, what we found was that missing values with 0 generally worked better for binary and categorical features. Using a smaller set of features with high variance was comparable to using more features from the unsupervised learning. Uh, Also, what we found was that shallow feed-forward neural network worked better than the deeper ones, and the final M score was comparable to those of the competition winners. Here are some of the other ideas which we want to try later on. Next. These
These
are
are our contributions, and thank you for watching.